Okay, so I hope I am audible, right? Please respond.
Yes, sir.
Okay, thank you. So I think we have those who wanted to join, they have joined, I think. Okay, so those who will be coming, let them, they will keep on joining, no problem. So I don't think that we should waste some more time. So rather we should start, I think, right? So, or shall we wait for some more minutes for your friends to join, or shall we start?
So let's wait for a while.
Okay, so then in the meantime, if you have any doubt from the previous classes, okay, or maybe from your class test to syllabus and all, okay, you can clarify those doubts. Okay, so it seems like no doubt. Okay, so in the previous classes already I have given you the introduction about the velocity and acceleration analysis and mechanism, why it is important, okay, what can be achieved through it and all, okay, and how they help in understanding about the motion of that particular mechanism that is under consideration. Similarly, how ultimately they helps in the construction, okay. So those things also we have discussed. So there itself. We have seen how these different terminologies like the acceleration, displacement, then velocity, then the acceleration, how they are interlinked. Okay, and knowing of one from another, how it can be achieved, and how it helps in determining the position in doing the position analysis, or maybe in the synthesis of the mechanisms and all. Okay, so those things already we have discussed. So there we have seen. If you recall, so basically we have said that basically we'll be limiting our discussion with respect to two main methods of velocity analysis. That is the relative velocity method, and another one is the instantaneous center method. And both of them are kind of graphical methods. Okay, so that means considering proper scale and all, and considering the proper unit, proper scale, and the proper direction. All these things are important, and after doing so, that means somehow using the logics, okay, proper logics, you will be able to find out the whatever is being asked in the question. Suppose a particular velocity of a particular point on that particular mechanism, how it is going to behave, what will be its velocity analysis and all, so that kind of thing. So later on also about the relative velocities between 2 points, that thing also we have discussed. Okay, so we have seen that basically how it's from your normal vector analysis. Okay, how you can say like PV. Suppose okay, so let's discuss. Okay, so suppose there are 2 points A and B, just like this. Okay, this is a point A, this is point B, and we are saying that this is VA and VB. Okay, B suffix B, they are nothing but their absolute velocities. So we have already discussed about what we understand by absolute velocity, what is relative velocity and all. Okay, and there we have understood that absolute velocity, whenever we are talking with respect to a kind of, you can say, uh, fixed position or zero velocity force point. Okay, so basically with that, with respect to that, okay, we discuss about this particular absolute velocity. And relative absolute velocity generally is a kind of constant term. Okay, and relative velocity, actually it is the velocity of a particular point relative to another one. Okay, and the relative velocity for a particular body, it may be different depending on which with respect to which particular other body, okay, you are talking about, whether that particular body, reference body, is a kind of a moving body, a fixed body, or in which direction it is moving, what is its velocity, magnitude, and all. Okay, depending on all those things, the relative velocity, it may differ. So now, as we have shown here in this particular diagram, okay, that is A and B point. Okay, they are having this in this direction. This is the BA. This is BB. That is the absolute velocities they have. Okay, and if I think that if you consider if the same amount of motion is given to both the points, and then there is no change in their relative velocity. Okay, so now that means what will happen in that case of relative velocity? Both of them will have the similar kind of motion. Okay, so in that case, relatively, it will be as if they are not having any motion. Okay, suppose you consider, suppose if suppose you are Suppose a car is moving at a speed of suppose 10 kilometer per hour, and you are running behind it at a speed of suppose 5 kilometer per hour. So then definitely you have got a particular relative velocity of with respect to it. Okay. And now if you give same motion to both the bodies, suppose you add 2 kilometer per hour in the same direction, and here also for you also suppose you are adding 2 kilometer per hour like that. Okay. Same motion will be given. Then also what will happen? The previously whatever was 10 kilometer per hour will become 12 kilometer per hour. Okay. And the other one previously which one 5 kilometer per hour will become suppose 7 kilometer per hour, and thus once again the relatively it will be seen that as if they have got the same relative velocity. Okay, so that is it. Now let in this particular case, okay, we are giving minus va velocity to both the point. Okay, as it can be seen, so va, this is the magnitude. Okay, and plus sign is along this particular direction, so negative sign will be, that means along this particular direction. So we are giving with this dotted line, we are showing that, okay, minus p to point a, similarly minus pa to point b. Okay, then that means there should not be, as we are giving the similar motion, so relatively they should not have. Okay, so now what will happen now, because we are giving minus va to point a also, so velocity at point A will become 0, and in case of your point B, it will become PB minus PA. Okay, that means the velocity of the point B, it can be expressed as the vector summation of PB and minus PA. Okay, it is nothing but it is defined as the relative velocity of point B with respect to A, and we write it like that. Already we have also discussed. So relative velocity of P with respect to A. Okay, if we write like this, PAB, then what does it mean? Relative velocity of A with respect to B. Or sometimes if we just talk about, suppose if we write PA directly, or maybe suppose PB directly, then what does it mean? We are talking about the absolute velocity of point A or absolute velocity of point B. Okay, that is that. So it can be seen here. So it can be also it can be written in the vector form as PB. Okay, so it is nothing but PA and the vector summation of PA. Okay, so this is PB, this is minus PA. Okay, this is the resultant PBA. So you can use any parallelogram law of vector addition or the triangle law of vector addition. So those things all of you already know. And similarly, later on we have also discussed about can say how we can get the point relative velocity equation. Those things also we have discussed. There we have seen that p equal to r omega, that expression. Okay, still we are going to discuss once. So now we already know rate of change of displacement is nothing but it's a velocity. Okay, and now whenever right now we are talking about the velocity relative velocity equation. Okay, so now this velocity factor generally is applied only for a particular point, specific point. Okay, and it should not be applied for a line, some volume, coordinate system, etc., or a collection of points. Okay, because the velocity of each point may differ. Because of that only we generally apply the velocity factor to a particular specific point. Okay, so point to point it may differ. Now see, our concern is to determine the velocity of the various links of a particular machine. Okay, so that the location of the points on the, and for that so the location of the points on the link is very important, because already we have seen that depending on the location of it. Okay, so basically we apply the velocity vector to the point. Okay, that means ultimately it represents the location of it. Okay, so now there are two basic situations regarding the location of the points on a rigid link. Okay, so one situation it may be that the rotation of a rigid link about a fixed center. In this case, one point is free to revolve about the fixed center. And second situation may be such that both the points are located on the same rigid link. Okay, so there may be two particular situations. So we don't know whether it is properly feasible for you people or not. Okay, I am zooming it. So in this particular case, you can see a figure. So where a point O, this is a fixed point, and this definitely is a rigid body. Okay, so this body is the rigid body we're talking about, and there is a point A located on the rigid body, and it is rotating about this particular point O. Similarly, now in this particular case, so this is the rigid body. Okay, that preform diagram is nothing but a kind of rigid body, and both the points A and B, they are located on the link body. Okay, that is the rigid body. Now, now, if you consider first figure, that is the rigid body, okay, on where there is a point A which is able to rotate about B, okay, rotate about a fixed center O, okay. So let's now consider a rigid link, maybe rigid body P, okay, rigid link. You consider rigid body, that is we are representing it as the rigid link, okay, rigid link B, and it is rotating about the fixed center O. Okay, so there is a point on this particular point A on this particular link. This is the point A on this particular link. Okay, and it is, let's consider it is at a distance of R. Okay, R from suppose O. It is at a distance of R from O. Okay, so and let's consider, suppose if we draw a line like this, the horizontal one. Let's consider line OA, this one, this is the line OA. Line OA makes an angle theta. Okay, let's consider it is making an angle theta with the x-axis. Let's draw this x-axis and let's this angle be theta. Okay, and now because of that, okay, let's consider whatever is this particular point A. Okay, now we are making a coordinate system. So let's consider suppose x a x suffix a, sorry, x suffix a, and y suffix a be the coordinate of this particular point. Okay, x comma y. Okay, x a y a for a point A. Now what can be written? We can write x a to be r cos of theta, and we can write y a to be r sine of theta from here. Okay, r cos theta is going to give you this. Okay, and r sine theta is going to give you this one. And from there we can differentiate it with respect to time. Okay, these are nothing but we are getting that particular positions actually from there. To get that we know this dx dt is going to give you like that particular velocity. Okay, so now we are differentiating x a and y a with respect to time, which gives you velocity. Okay, so x a dt, similarly dx a dt, dy a dt that we are doing, and this is r is constant. So for cos theta, it will be minus sin theta, and this is with respect to t, differentiating with respect to t. So this is the variable previously theta. So on d theta dt also will remain. So it is going to give you minus r, and this d theta dt we know. So it is rate of change of angular displacement. So it will going to give you the angular velocity omega. So that can be replaced. So minus r, it will become r omega of sine theta. Similarly, for this case, so it is once again it will become r omega cos theta. Okay, and now this is nothing but this gives you the velocity of point A in x direction. So we are writing like absolute, it is VA, x represents the x direction. So that is nothing but the absolute velocity kind of thing. Okay. Similarly, here dy a dt, it's nothing but the velocity of point A in y direction. So VA superscript y. Okay, denoting like this. And omega we already know it's angular velocity of OA, that is the link. So from here what we can get? So the total velocity, this is basically about in the x direction, this is in y direction. So total velocity can be obtained as root over d square plus this velocity square. Okay, because they are orthogonal in direction. This is x direction, this is y direction. Okay, so this is 90-degree reference, they are orthogonal, so we can get the total velocity as this. Okay, so root over v a square plus b square like that. Okay, so that because the theta will become 90 degree here. So what we will get? So ultimately we have seen that it can be obtained as v equal to r omega, and this relative velocity equation is very important. Similarly, as we know, this velocity is nothing but a kind of vector quantity. So the direction also is important, and the direction of the velocity of point A with respect to this point O, it's a perpendicular. It's very important while doing the while solving those problems and all. Okay, drawing the different velocity diagrams, etc. for different mechanisms. Okay, so it will be important. This knowledge will be important. So the direction of velocity of point A with respect to O, it's perpendicular to the line joining point O and A. That means VA is perpendicular to OA. Okay, so now if you look at this particular figure, so this one was the OA. Okay, so this way it is OA, so VA will be, that means perpendicular to it, so somewhere in this direction. Okay, so it will be perpendicular to it. Okay, depending on whether it is rotating in clockwise or anti-clockwise, you are going to get that particular direction. But right now, this way only it will be there. Okay, so this is the line, so it should be perpendicular to this particular. That means if you extend this particular concept to the different links of a particular mechanism, then for a particular link, previously we are drawing this like a rigid body, we are denoting the link with respect to a rigid body. So if you think about the configuration diagram, those things already we have discussed previously, what we understand by configuration diagram and all. Okay, so in that case, if this is the link can denote, then in those cases directly the perpendicular direction you can consider. That means for the links it will be perpendicular to the link. Okay, so that is the velocity direction. Similarly, the second condition may be also in the similar fashion it can be done. Okay, relative velocity equation for 2 points which are on the same rigid link. So in that particular case, what will be the difference? Okay, so suppose if we are talking about coordinate of point B, then the then we have got this addition. Okay, and rest is somewhat similar. Okay, so point B is at a distance from point A. If you look at this particular figure, okay, so B and A it is there. So after that, rest is similar. Rest is similar way we are doing it. Okay, so but here velocity of both the points will come, and once again, now this PBA it will represent the relative velocity of point B with respect to A. Previously, as the point O was fixed, so that itself became the absolute velocity. Now it will be the relative velocity equation that will have. So PB it can be obtained as the addition of VA, factor addition of VA plus that R omega. R omega is nothing but that velocity of P with respect to A. So PBA means how to read it? Velocity of P with respect to A. Okay, so this is, and as A and B both none of them are fixed points, so it is the relative velocity. Okay, so this is the relative velocity. After this was understood, not absolute. Let me know the easy concept. This is not absolute velocity, this is relative velocity. Understood or not? So that means, just like previously we have discussed, if the 2 points are A and B on the same rigid link, the velocity of point B with respect to A will be perpendicular to the line joining points A and B. And magnitude how to get, so it will be v equal to just from the r omega. So r is, in that particular case it will be that a b, that particular distance, and omega will be the angular velocity of that particular link. Okay, so omega into ab, that will give you that velocity magnitude, and direction will be the perpendicular to the rigid line. Okay, so this concept we are going to use now for drawing the uh, velocity diagram for the slide recurring mechanism. Simple mechanism that we already know. It's a very simple mechanism, yet very powerful, useful one. So up to this much you have understood or not, let me know.
Yes, sir.
Okay, others, what about others? I hope it's a yes for you also. So now we are going to use this relative velocity method to find out the velocity of various links. Okay. Now first we'll be talking about the slider crank mechanism. Okay. I hope all of you already know slider crank mechanism, and all of you can recall that particular configuration diagram for slider crank mechanism. So here we are showing the slider crank mechanism here. So what is this particular link? What is this link? Who will tell me? What are the various names for the different links which are present in the slider crank mechanism? How many links are there in slider crank mechanism? Centering down. Tell me how many links are there in the slider crank mechanism?
Sir, I guess two.
Two links in slider crank mechanism. Norangsi, what do you think? Is he correct? Centering down.
Sir,
Norangsi,
sir,
yes, please can you repeat because your voice was distorted.
uh, uh,
Okay, I think some network problem is there. Ziggyas, what do you think? Hello,
Sir, two.
Ziggyas. Two links. Assis, in a slider crank mechanism, how many links are there? If you could forget everything, these are very simple and basic
Four.
things.
Sorry, sir,
Biswajit
four.
is saying four, right?
Four, sir.
Uh,
Sir, connecting
yes,
road
it's
one ছিল, sir.
four. So, yes, it's a very basic mechanism. All of you, even in your sleep, you should be able to draw it, nomenclature, like properly. You should be able to have the labeling of it properly. Even if whenever you are dreaming, then also the slider mechanism it's working. What are the various links present, etc. Those things should be in your mind. It should be very, 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 very vividly clear. Okay. So now, who will tell me what are the different links? Anyone? Yes, this is
Sir
there. Okay.
AO,
Okay.
Sir AO, AB, that connecting rod, then slider, and then hinge joint.
Hinge joint is a link.
Oh no, sorry, not joint. That what is this crank connecting rod and that slider?
Then only you have said only three.
Sir, the frames
Pandit,
are.
Oh, frame, yes. No, frame. So
yeah, Tapas is saying something, or who was saying?
Yes, sir.
Yes, please Tapas. All the four links. You also agree there are four links, right?
Yes, sir.
Okay. So just with respect to this figure, just let us know. So this OA, it's a link.
Mm,
This one.
s- yes, sir.
What is the name for it?
Sir, it's wait, sir.
crank.
Yes,
Crank,
correct.
sir.
Uh, it's a crank, right? Then what are the other links?
Sir,
This
Connecting
one,
rod
B.
slider.
Sir,
this is already written.
yes, sir.
Written, no problem. So AB, that's the connecting rod. Already in figure itself it is there. Okay. Then this portion is this is nothing but the slider. It is able to slide in this particular guide. Okay. So now this guide and this fixed position, they are the fixed link. Okay, fourth link.
Yeah,
Okay.
fixed link. Yes, sir.
Frame
That's what I was
frame.
telling. Hinge joint. Yeah,
Yeah. Hinge joint is not a link.
means the joint is connected to that surface. No,
So
that's
basically here we are talking about this particular frame. Okay. But this is also having the similar thing. Okay. So that is the thing. These things about slider thing people should not forget how it is working. Or who will tell me what are those who said there are two links? You tell me some application of this slider frame mechanism. Those who said four links, no problem. Centering down. You let me know some of the application of this slider frame mechanism. Practical application.
Sir, quick return mechanism.
Quick return mechanism. It's the application of slider frame mechanism. From the name itself, you can say, na, both of them are two different mechanisms. I'm right now asking you about practical application. Where do you generally see the slide diagram mechanism, application of slide diagram mechanism? Very basic answer, some very basic situation. Who had said, I think Ashish said two or Jigyas said two links. These things you should not forget. Then otherwise there will be very problem. All of you are like, it's like there is a popular saying, na, okay? You have completed the Ramayana, reading the Ramayana, now you don't know Sita was it's a character, male character or female character, or Ram male character or female character. It's something like that. It should not happen. So see in the IC engines and all,
Piston
that means
cylinder arrangement,
yeah,
sir.
piston cylinder, that is nothing but a kind of application of this slide diaphragm mechanism itself. Apart from that, there are so many applications. Okay, so we should not forget these things. Okay,
Sir,
so now how? Yes, Vishal.
sir, is hand pump a slider crank mechanism?
There is a inversion. We have also studied about
Yes,
inversions,
yes,
right?
inversion, yes.
Yeah. So
Okay.
we also have got inversion of slide diaphragm mechanism, or
Yes,
for
sir.
other mechanisms also we can have different inversions. Okay. So
Okay.
but the basic thing is like this. Okay. So now yes, I thought that it will be very easy. Okay, but if people forgot how many links were there in slide diagram mechanism. Now, will you ever forget now? Those who made the mistakes, censoring the
No, sir.
now it will remain in your mind, right?
Yes, sir.
Okay, then just what are the different links? Okay, properly you just name one second. Yes, Senchindo,
Pardon,
whatever
sir.
you have just yes, the same question I am asking you once again. I have already given the answer. You just let me know once again. For us, okay, for all of us, okay, just let us know the proper answer once again. So there are four links in slide diaphragm mechanism. Okay, name them with respect to this particular figure, maybe.
Sir, crank, connecting rod, slider, and that fixed part.
Now we have got the frame, right? So how what are the various motions there, how it works? So crank, what kind of motion does it have? So here it is. What kind of joint is this? This is a pin joint or hinge
Revolution.
joint. Okay, so or okay, revolute joint, similar kind of
Yes,
hinge
sir,
joint. Okay,
revolution.
pins. Okay, so that means it can have what kind of motion? This is a pin joint, pin or hinge, or ultimately it constitutes a revolute pair. Okay, so pin or hinge. So about that, that means this can have rotational motion. That crank can have rotational motion. Okay, so similarly here it is pin joint or hinge joint. So right now this is not a pin joint or hinge joint. We are just denoting another point C on this particular link because we are right now interested in the velocity analysis of this particular with respect to this particular point. Okay, that means, and similarly, this is the slider that we have. It is able to slide in this particular frame. Okay, so the rotational motion of the slider of the crank can be transferred, and we can get reciprocating motion on the slider within this, and how it is constant to move only in this particular direction that we already know, right? So this is the line of stroke direction. Understood? Those words you should remember. So this is nothing but the line of stroke direction. Okay, we call this movement of this slider as the stroke. Okay, it gives you different strokes. Okay, and this is nothing but the connecting rod. The connecting rod, it joins the this particular end point of this particular crank, okay, to the slider, and they are hinge joint. So they constitute revolute pair, okay. But here this slider with respect to the guide, it constitutes sliding pair or revolute pair. What kind of pair?
Sir, question.
Slider.
Question, sir.
This yes, the slider, and suppose slider where a link one, suppose, and suppose this guide is suppose link two, okay. Then link one and two, that is the slider and the guide. What kind of pair it is constituting?
Sliding pair, sir.
Sliding
Yeah,
pair,
it is
sir.
sliding. Correct. And here in the pin joint, suppose if this is fixed, this
Revolute,
fixed portion is suppose one.
revolute pair.
Yes, correct. It is having turning pair or revolute pair. Okay, so those things you should remember. Okay, so now actually our intention is to we are by using the relative velocity method. Okay, we wanted to analyze this particular slide recurring mechanism, and now this particular velocity vector diagram, okay, or the velocity diagram. Okay, so now why previous in the previous classes, if you recall, so I have told you that this while we do the acceleration analysis or velocity analysis, after that then I will go for acceleration analysis. So in those cases, actually, this diagram, these are graphical methods only, and they can be utilized to know or to have the knowledge of the velocity of different points which are there on this particular link. So now we can consider a point which is C, okay, this point C which is there on this particular connecting rod, and we may want to know about its function. Okay, so now considering suppose this slide occurring mechanism, and if even if this particular figure is not given and directly it is said that you have to analyze particulars, do the velocity analysis of a slide occurring mechanism, then also you should be able to draw this configuration diagram for slide occurring mechanism, and after that you should be able to do the by using, if it is said by using relative velocity method. Right now that is what we are going to discuss, so that way you should be able to do. So now it's required to draw the velocity diagram, and for that particular case the angular velocity of the link OA, that is the crank, that is given, it is shown here, it is the omega is shown in this particular direction. Okay, so this is clockwise motion is shown here. Okay, and we are interested in drawing that particular velocity diagram, and that's what we can get. So actually by utilizing the proper knowledge of it, okay, so we'll be able to get the velocity of different answer point, okay, on that particular mechanism, any point. Okay, so that is what is the beauty of this velocity diagram. So now to draw the velocity diagram, okay, how to start, how to do. So now, as these are all what kind of method? Analytical method or graphical method? This is graphical method, right? So graphical method means what?
Graphical method.
Yes, correct. So graphical method, and if it is graphical method, scale is very important, right?
Yes, sir.
Considering scale is very important. Considering a proper scale is very important, and after that only, okay, when you do it which considering the proper scale, then only whenever after drawing that particular figure, when you want to have the relevant data, okay, you want to extract the relevant data from this particular suppose velocity diagram, then only it will be useful if you draw it in using proper scale, because once again you will be taking suppose the lengths etc, will be and measuring the lengths etc, and you will as per the whatever is the previously considered scale, you have to convert and get the answers, okay, so that's why considering the proper scale is very important, and you have to mention it, and mention it only if you just consider the proper scale, and in your mind only it is there and where it is being mentioned, then the other person who is looking at your diagram and trying to analyze or extract some data, he or she will never be able to get any proper valid data, because he or she doesn't know what's the scale that you have considered, how to do the conversion, that means what is the conversion factor. Conversion factor means right now if we are saying that we are going to draw the velocity diagram, then we are drawing this kind of diagram only, and we are representing velocity with it, right? So that means some suppose I'm just giving example, okay, arbitrary example. Suppose 10 kilometer per second, okay, or 10 kilometer per hour, or that kind of velocity. Suppose, okay, that you are drawing in this particular figure as suppose 10 centimeter, and if you don't mention it, then people will not be able to understand whether that 10 centimeter denotes 10 kilometer per hour or 20 kilometer per hour or whatever be it. Okay, so mentioning that will be very important. Then only after you do it, and or maybe you yourself later on you check or someone else goes through it, then by considering that proper conversion factor from that scale, he or she will be able to extract the data, or maybe he or she will measure those values, okay, measure the length and convert as per the proper scale and get the required data. Okay, up to this much if it's clear, is it clear why this is very important, proper considering proper scale and all? I hope yes. Okay. Now, as you can say, uh, we're saying that the velocity of point there, that angular velocity of the link, okay, link OA, that is given. Okay, this is the link OA. Angular velocity is omega, that is in this particular direction, that is given. Okay, that's the given data. So now after knowing this, okay, how we can start. So we see, so from there what we can have, so this velocity A of a point A, this is a point on this particular link OA, right? Yes. So point A is lying on this particular link OA, right? So now, and what is the length of this particular link? That is nothing but this OA is the length. Okay, some numerical value will be there. So from there we can get the velocity of point A. How to get the velocity of the point A? How can get? So for that we can use the knowledge of this omega. We know that V equal to R omega. That expression we already know. Okay, so V equal to omega R. Okay, so in this particular case, the link length is this OA. Okay, this itself is behaving like this particular R. Omega is already given. So that means the velocity of that particular point A, that is VA, can be obtained. And the SO here is a kind of fixed point. So directly it denotes like the absolute velocity. So VA can be written like this. So it's a, we can write V suffix A as omega into O A. Okay, just like V equal to omega R. And what will be the direction? So it's a in the clockwise sense about O. And VA, it is perpendicular to OA, that particular link. Already we have discussed. So that velocity, the numerical value, magnitude can be obtained by V equal to R omega, and the direction will be perpendicular to this particular link. That means that is the initial known thing. So we can start from here. So for doing so, doing that particular velocity analysis, so in the velocity, we are going to draw the velocity diagram. So in the velocity diagram, will denote these points with the small letters. So in this particular configuration diagram, the points are denoted with capital letters. Okay, so while starting drawing that particular velocity diagram, we'll start with that particular known knowledge. Okay, that is V equal to R omega, using that, and we'll get a particular value. Okay, numerical value we'll get, and the direction we have obtained. So right now we are not considering in this particular problem any numerical value, but while solving some problems, you might have you might be given that values. Maybe suppose crank length is suppose this length. Okay, suppose connecting rod length is suppose this, or it is making an angle this much with respect to suppose this, or like that. Okay, that kind of numerical values can be given, or it is rotating with an angular velocity of this much radian per second. So in that particular case, so from this data you will be able to get a numerical value of VA, and that you can consider as a proper scale. Okay, you can consider a suitable scale for that particular value of V, and you can start drawing. Now how to draw? So now for drawing, okay, so how to draw the velocity diagram or the velocity vector diagram? So we'll start with a point O. You consider, if this is the pace, you consider any convenient point O. Okay, so O represents with respect to this. We are starting with that particular fixed point O. Okay, so take any convenient point O. This is the O point, and you have to draw the vector OA. We are going to use the small letters only. Okay, draw the vector OA such that OA is equal to this. OA itself is equal to that particular numerical value of VAO, which is nothing but equal to omega into OA. And what will be its direction? It should be perpendicular to OA. Okay, so now that means initially drawing this diagram, initially having this configuration diagram is important. Then only with respect to it, what will be, whatever be the position of suppose this particular crank. Okay, so you should be able to have a perpendicular direction to it. So we are starting with this. Okay, start, we have taken a particular point O, and we are going to draw the particular, suppose we have already found out VA. right? So velocity of point A we already have omega into OA. So we are going to draw the OA vector, okay, which will give you V, which is equal to VAO, this particular value. Okay, so we are going to draw. So this was the link position. So perpendicular direction is something like this direction. Okay, so this way we are drawing the vector as per the scale. Suppose if this mass is 5 centimeter, we have to draw 5 centimeter and direction is perpendicular to this link. Up to this mass, is it okay? Let me know. Hello?
Yes, sir.
Okay, so done. Next, what is the knowledge that we have? So now, once again, this AB, so this is the point B, okay, and this is A. Now AB also is a rigid link in this particular mechanism, right? So in this slide diagram mechanism, AB, that is the connecting rod itself, is a rigid link in this mechanism. Now once again we know velocity of the points which are there on this particular link AB. Okay, so if you can consider, so velocity of point B with respect to A. So how to write it? Velocity of point B with respect to A, that is VBA. Okay, so now if we want to have this particular VBA, that is the velocity of point B with respect to A, then once again we know that we might not be right now knowing the values, just like v equal to, we cannot use suppose v equal to r omega, that kind of value, okay, that numerical value right now I don't know, but I know that direction of it. I know it's a rigid link here, and for that the direction of velocity is always perpendicular to the link itself, right? That much knowledge we have. So now previously up to A we have already obtained as per whatever is the value. So now AB itself is a rigid link. Okay, both the points A and B, it is lying on this particular AB link itself. And if we want to discuss velocity of point B with respect to A, so the direction is perpendicular to this particular link direction. Okay, and this is the link direction. So perpendicular to it, we have to have this particular PBA. So now from A, starting from A, because A is also a point which is lying on AB link. Okay, so starting from this small A, okay, we'll draw a vector which is also perpendicular to the link AB from here. So this way, passing through point A, we have to draw a line. Okay, right now I don't know what is the magnitude of it, but I know this is the direction. Okay, for the previous case OA, I knew both magnitude as well as direction. That's why the point, whatever O and A point, okay, that is definite point. But right now I know B point will B point will lie somewhere in this particular line. Okay, but right now I don't know what is the exact location of B. Up to this much, okay? Let me know someone.
Yes, sir.
Okay, thank you. Now next, another logic is, see, B is the slider, right? Okay, and in which direction it can have the motion, in which direction it is having the velocity. So it always slides along the line of stroke direction, right? The slider will slide along the line of stroke direction only, we already know. And this dotted line, that is, it is shown here, okay, that is nothing but the line of stroke direction for this particular slider, right? All of you agree with me? Slider is sliding like this.
Yes, sir.
Okay, that means if it is sliding like this, okay, it's a kind of linear motion that it has got, has got. So the velocity also will be in that particular direction itself. In which direction it is sliding? Okay, that means in this direction itself it's moving. That is the line of stroke direction. So what we will do now? So starting from O, we are going to draw a line which is parallel to this OB, this line OB. Okay, and when we draw this, it is going to intersect somewhere. And wherever it intersects, actually, that is nothing but the location of the point B. Previously, I didn't know. I only knew that velocity of B, okay, it will lie somewhere along this line only. on this line only. Okay, because that is perpendicular to link AB. Also, I know velocity of B, that is slider. Okay, it is having velocity in the line of stroke direction only. So from the starting from O, I am drawing this particular P for PB. I am drawing it. Okay, that is nothing but the PB velocity of absolute velocity of B with respect to O, because O is fixed point. So if this is B, so this line, this vector OB will represent small ob, that is this vector ob. Okay, it is representing absolute velocity or relative velocity for B. Who will tell me? O is the
Sir, can
fixed
you
point.
repeat it?
So this line OB, okay, now I have already located point B, because I have said that it should be lying on this particular line, okay, this line, and also from another logic we have obtained it should be parallel to this also, okay, this way also. So wherever they both of them meet, that is this particular point, that is nothing but the point B. Okay, starting from O. Up to this much, all of you are okay with me?
Yes, sir.
Okay. So now what I am just asking is, if I consider this vector OB, it has been written here. Okay, OB vector, small ob. So it's you know that it's a kind of some velocity of B only we are talking about. But is it the absolute velocity of B or relative velocity? O is fixed point. I am giving you the hint.
Sir, I think absolute, sir.
Yeah, it's the absolute velocity of B, or I can write directly V of B. Okay, because it is, if you discuss with respect to relative velocity, it is relative velocity of B with respect to O point, and O is fixed point. So with respect to fixed point, if we discuss something, that itself is kind of the absolute velocity. Okay, so that completes the velocity diagram. Okay, now depending on in which direction you are considering the direction. Okay, so this way if you consider, that will be velocity of B. This is the A point, this is A point, okay, and this is B point. So this line, this vector is going to give you VBA, velocity of B with respect to A. Opposite direction if you consider VAB, velocity of A with respect to B. Okay, understood how we have drawn this? These are the main steps. Let me know.
Yes, I understood.
Okay. Now, once we have this particular velocity vector diagram, now you can have, if you consider any point on those links and all, okay, you can, considering this particular diagram, you can get, suppose if you consider point C, which is lying somewhere here on this particular connecting group, and you want to know how it is behaving, what is its velocity, then from this diagram you can have it. So what we will do, whatever is the ratio, okay, at whatever is the location, that means location of point C on this particular link connecting rod, that is the connecting rod, on the connecting rod, and some point C is here. Okay, so now what we will consider, whatever be its ratio, suppose from B whatever is this distance, or from A from this side whatever be its distance. So in this diagram, that point can be located at that particular ratio. Suppose if this mass is suppose 2 unit, okay, and this mass is suppose 3 unit. Suppose this mass is 2 unit from, and this one is 3 unit. Okay, that means point C, it is located, it is at a distance of suppose 2 unit from point B if I consider, or if from this side if you consider 3 unit from suppose B. So now here in this particular figure also, accordingly, suppose that particular consideration you can have whatever be its particular distance, and if you want to know about its absolute velocity, we will join that particular point location C with O is the fixed point, and that means this particular vector if we draw, so this vector will give you V suffix C, Vc, that is the absolute velocity of C with respect to O, that is nothing but, that is the fixed point, so it's a absolute velocity. Okay, so that is the thing, or maybe any other point if you want, that way you can obtain, or the relative velocity if you want with respect to some other point, you can have like that. Okay, understood? That is how it is important. So that is what is being written here. So the velocity of any point C which is located on the connecting rod AB, it may be determined with this particular relation. So AC by AB, okay, that is from the velocity term, so can be obtained in the same ratio as that of its length, that is AC by AB, or AC equal to AB into, that is the vector AB vector into AC by AB. Okay, so that is what is the thing. Similarly, angular velocity of the connecting rod AB, so it can be obtained right now. We can determine with the help of once again V equal to R omega. Okay, that particular we can go. So here now omega of AB, that means will become P BA by AB. Okay, that particular will give you that particular angular velocity. Thus, we can get to know, we can know, or we have already analyzed the velocity analysis. We have done the velocity, relative velocity analysis of slider crank mechanism. Okay, so with this, we'll stop here for today. You let me know whether you have understood today's class or not.
Yes, sir.
Okay. So then thank you everyone for joining. So we'll be meeting in the next class.
Thank you.